Okay, so this next page that we're looking at here says, can we find instantaneous rate of change? So the other day I used the example for average rate of change. It was like if you drove from here to Winston and it took you an hour, right? And it was 50 miles, and that was 50 miles per hour was your average speed. So we talked about the fact that that probably was not your speed most of the time. You were probably going faster at some points and slower at some points. But if you are driving down the road, can they find your instantaneous rate of speed? Your speed at that moment. Perhaps if you're driving past a police officer that has his radar gun out, right? He can find how fast you're going right at that moment. And if you try to tell the police officer, my average rate of change has been 50 miles per hour on this trip, is he going to care if your instantaneous rate of speed was 95 miles per hour going down 77? He is not. He or she is going to give you a ticket. And if it's 95, you're going to be in big trouble. You might not be driving anywhere anymore. So instantaneous rate of change you can think of as like that radar gun speed. It is your speed at that second, right? So for these blanks right here, this is really a calculus idea. What they're doing, a lot of what they're doing in the AP this class is called pre-calculus. A lot of what it is supposed to do is prepare you for calculus, give you the tools that you need for calculus. So this is something we talk about big time whenever you get to calculus, and we're just kind of introducing the idea here. The idea of instantaneous rate of change is equivalent to finding the rate of change of function of a function at a given point. This concept is developed formally and used in calculus, but we can approximate the rate of change at a point by using the average rate of change over small intervals. So, in order to find the exact instantaneous rate of change, you have to know how to do calculus, which hopefully all of you guys are going to learn next year in the most wonderful calculus class, because calculus is my favorite. But we don't know calculus yet, so we can't find the instantaneous rate of change. But we can get pretty close to the instantaneous rate of change, because I know we can't use Desmos, but Desmos is still so helpful to picture things. I'm going to graph what we're about to look at right here. We are looking at this equation, h of t equals negative 4.9 t squared plus 25t plus 5. And, gosh, Desmos is so easy, isn't it? I'm going to make this 50. Okay, there's our beautiful graph of what's happening right here. And we're looking for it looks like everything we're looking at here, we're looking at 1, right? All these intervals start at 1. So if I type in 1h of 1, it'll put me a point right there. We're looking at that point right there. That's where my x equals 1. So I'm trying to think about how steep that graph is at that point, right? Now, just looking at it, it might be harder to see, but if I zoom in really close to that point, does that look like a curve anymore? Not really, right? It looks like a straight line. So if I can get really, really close, like for example, this first one is 1.1, h of 1.1. Is that my graph? I might be in too close. No, maybe I'm not in close enough, maybe. No. Why is that not showing? Well, no. Maybe I am. Let me go back. Okay, yeah, there. So if I get, like, the line between those, it is technically curved a little bit. Does it look curved? No, not really, right? So if I want to find the slope between this point, it's not going to be the exact rate of change. It's going to be pretty close, right? What about if I do this next one, 1.01? That's the purple dot right there. Well, that is even closer, right? That line is even a little bit straighter right there. That's going to be really close to my actual value. And then if I do 1.001, that's that black dot, even closer, right? So if I find the slope of this line right here, it's really, really close to the actual slope of the line at that point because it's so close to being the slope right there at that single point. So let's split the work up on this a little bit so that we don't have to do all 4 of these. Let's see, Alyssa and Courtney, right? You guys do A for me. I want you to find the average rate of change from 1 to 1.1. So you would be using this equation, and you're doing the interval from 1 to 1.1. Definitely can use your calculator on this. Let's have you 3 right here. You guys are going to do B for me. I want you 4 right here to do C for me. And then back row, you guys do D. All right? That way we won't all have to do all 4 of these. Second quit. All right. So definitely one thing you can do is just you can do negative 4.9 times 1 squared plus 25. Like all of you are going to have to do this, right? Because you, all of you have to find that point because 1 is one of the coordinates that you're looking for. So we know that one of the points here is 125.1, right? And everybody's going to be using that. Let me show you a trick on the calculator, particularly if I was making you do all 4 of these at one time. Watch this. This is just kind of cool. I'm going to type in that equation, negative 4.9x squared plus 25x plus 5. Okay, I'm going to put my equation in. All right. So I want to plug in. I want to find h of 1 for that. So since that's stored in y equals, I can do this. If you hit, I'm going to write this down, vars stands for variables. You're going to go over to y vars. So hit the over button to go over to y vars. And then you want to choose one function. Okay? And it's going to give you a list of all your y1, y2, y3, y4. I put mine in y1, so if yours is in y1, you're going to choose y1. Or if it's in a different one, you would choose a different one. So if I do y1 and then do parentheses of 1 like that, it'll plug that number in for me. If you only have to do it one time, that's a lot more steps. But watch what I can do. I can do y1 of 1.1 now, and it's going to give me the answer. And I can do y1 of 1.01. Oops, I didn't put my parentheses. And it'll give me my answer. So it's helpful when you got to do something repetitively with an equation, so that you don't have to plug it in by hand every time. But plugging in by hand still works, so if you don't use that, it's fine. I mean, it's not quite as easy as just doing h of 1 on Desmos, but it's a little faster. What did you guys get for your rate of change? Okay, that is what I got also. So if you didn't have that, write that one down. That's the rate of change for that one. What did you guys get right here?
15.151, or he rounded and got 15.2.
Like I rounded up not that final answer. It was like
Yeah. So
I did to the third thing.
yeah. So that is actually a really good point to make. You really want to wait till the end of the problem to round the answer, because if you round to 3 decimal places during the problem, it might be off by more than 3 decimal places at the end. So so it's really probably the best practice just not to round at all, to like keep using that whole big decimal till you get to the end. Which, those of you with the old calculators, it's a little more hateful. Like, let's say that we've got, yeah, 2 divided by 7 or something like that, where you get this big decimal. If you got the new calculators, you can just go up there and grab it. But if yours is one of the old ones, if you do second negative key, it'll pull up the answer from the next line, and then you could do something with that. Yeah. Okay, let's see. Over here, what did you guys get for your rate of change? 15.1951. That is also what I got. If you want to round that to just 195, that'd be fine. But keeping more decimals is always good, always fine for that. And how about back here? What did you guys get?
Well, I rounded during the problem, so I ended up with just 15.
Okay.
I rounded to 3 here.
Yeah.
Somehow I got 1,000.
Ooh, that's not right. Ayla, any luck? Okay, same thing. Okay, so let's go through the process for this one too to make sure everybody's with me on this. So we H of 1 already did, and we got 25.1 when we plugged in the 1. So that means the point we're dealing with is 125.1. You have to do the same thing for your H of 0.999. And let me show you guys this. Also, for the purposes of doing a free response question, if it is a calculator active question, you don't have to show all your work for plugging stuff in. You need to write H of 0.999 to show the grader that you were plugging 0.99 into this equation. But you can do the rest of it on the calculator, so you don't have to write down the negative 4.9 times 0.999 plus all that. You don't have to write that part down. You can just write down the answer, because if it is a calculator active, they're going to assume you're doing that on your calculator. So we're going to do negative 4.9 times 0.999 to the second power, or squared. I could hit the square button. Plus 25 times 0.999 plus 5. And I get 25.084791. And I'm going to keep that whole decimal right now. 25.084791. There. So that means that point is the point 0.999, 25.084791. Right. So whenever we plug into the equation, it gives us the coordinates of our point. And so we want to do slope formula with this to find that average rate of change. So we'll do 25.084791 minus 25.1 over 0.999 minus 1. There. And so in the calculator, if you got the newer calculators, you can just hit the up button. It's going to grab that number and you can use it. Or if you have the older calculators, if you hit the minus key, it's going to automatically subtract from what was before it. It's going to put that answer up there. So we'll have that minus 25.1, or you can just type the whole thing in. So we got that. Make sure you hit enter. And then we're going to divide by I'm going to use some parentheses here, 0.999 minus 1, or it's going to be negative 0.001 there. And so we get 15.2049. So, all of these are sort of estimates of what we were looking for, right? Let me go over, do I still have that Desmos up? Shoot, I closed it. Well, I'm not going to type it back in for that. But which ones did we say would be the closest to the real value? It'd be those values that are closest to 1, right? So if we really look at these two right here, we've got 15.1951, and this one is 15.2049. What do you guys think the real value would be? 15.2. And if you knew how to do calculus, you could show that guaranteed it is actually 15.2. But 15.2 is right between 15.19 and 15.2. So that would be a good estimate. Now, at this point, we're just estimating because you guys are not going to know how to do calculus yet to be able to find that exact value. But it's going to be kind of close, right?
We're having like the 25.08 over the 20 minus the 21.5.
Mm-hmm.
We can just have everything in the calculator like completely over 999 minus 1.
As long as you put parentheses around the top and parentheses around the bottom. Yes.
Right.
Yes. Without the parentheses, it'll give you the wrong answer. But as long as you have parentheses on top and parentheses on bottom. Yes. So, questions? So the main idea here is if you get slopes really, really close to the point that you're looking for, that it should be close to the point, the slope at that exact point. Okay? This is not something I'm going to ask you to do a lot of. It is an idea that I'm interested in more so than like I'm going to have you do this 15 times. We split it up and it still took us forever to do this problem, right? Let's talk about that idea a little bit more. The rate of change of a function at a particular point is the rate the y values would change if the x values changed at that point. Think about that change in y over change in x you've probably seen before. Depending on who you had and what they did you do like the delta y over delta x? Have you seen that before? The little triangle that means delta. This delta symbol right here is used a lot in math and in science to mean change in. So you may see me write that a few times. If I've got triangle y over triangle x, I mean in change in y and change over change in x. This concept later in calculus, we're going to call it the instantaneous rate of change. We, at this point, cannot find instantaneous rate of change that I have said, but we can estimate the rate of change at a point by finding the average rate of change over a very small interval that's close to that point. We also can estimate rates of change at 2 points by estimating individual rates of change given the concept of a tangent line. So let's talk about what a tangent line would be. You guys, everybody's probably heard the word tangent before. It is sometimes used in just everyday language, right? Somebody will say that they go off on a tangent, right? In fact, I've got a really cool new math shirt that I got for Christmas that I need to wear sometime soon. It's in the wash though. I haven't got it clean yet, but I'll wear it next week sometime. But the idea of a tangent line is going to be, you do talk about tangents a little bit in Math 3 when you do circles. Does anybody remember what a tangent was? It's been a while. Okay, a tangent is going to be a line that touches a curve just at one point. So when we were talking about circles, the tangent line looked like this. It was a line that just touched that circle at one point right there. That is a tangent. The idea we're going to think about is like if we have a graph, right, and we want to know the slope of that graph at, let's say, this point right here, that point, that instantaneous rate of change at that point, we can think about the line right here that would touch that graph just at that single point. This is also called a tangent line. And it's actually like one of the biggest ideas in calculus, all derivatives, which is like, 3 of the 8 units in calculus all deal with this idea right here. So certainly we're just thinking about the idea briefly here. We're not going to go into all of it. But if f has a positive rate of change, if that tangent line would have a positive slope, the graph will be increasing. If it has a negative rate of change, the graph will be decreasing. All right, so like if we did a tangent line over here in this section where we are decreasing, our tangent line would look maybe something like that. It would have a negative slope on that line. So let's talk about some scenarios. This is just general thinking about things. We want to know if we have a positive rate of change or a negative rate of change in this case. So A, we are looking at a child's age versus the child's height. Is that going to have a positive rate of change or a negative rate of change? Should be positive, right? As the child gets older, so as age increases, child's height should increase, right? So that is positive. Right? Okay? And it is important, I guess, there that it said child, because if we were talking about adult, that would no longer be true, right? As your age increases, your height should not increase anymore. In fact, as you get old, shrink just a little bit sometimes. Everything's just compressing there. Gravity is having its toll on you there. So child is important in that as well. All right, a golfer's skill level versus the golfer's score. So as you get better at golf, your score goes up, it goes down, right? If it was a different sport, it would be up, right? Like as your skill in soccer increases, hopefully the score for your team also increases, right? But for golf, as you get better, your score goes down. So this would be negative. It makes you think positive because it's a positive thing happening, right? Like you would win more, but the score, the number would go down. Okay? The height from the ground of a coin dropped off. I always forget how to Burj Khalifa. This is the tallest building in the world. It's in Dubai. Yeah. If the height from the ground of a coin dropped off the Burj Khalifa versus the speed of the coin as it falls. Okay. All right. So height. So let's think about it because this one's confusing, right? What's happening to the height? Height is decreasing. And the speed would be increasing. Is that a positive or negative relationship? It is negative. If they are in opposite directions, it's going to be negative. Most of the time, we talk about the first variable increasing and the second variable decreasing, which is much easier to think about it being negative. In this case, it's kind of backwards because our first variable, our height, is decreasing. But because they have an opposite relationship, one is going down while the other goes up, that is going to be a negative relationship there. Okay, questions there? All right, here is a picture of a tangent line example. Okay, so the graph of f is shown above along with the tangent to f when x equals -4. So this line right here that they've drawn in here, this is your tangent line. Okay. In calculus, we're going to learn that slope of the tangent line is given the true rate of change at that point, that instantaneous rate of change. In AP Calculus, we can't find it exactly, but we can sketch them and estimate, right? So, example 6 says to estimate the rate of change of f at x equals -4. So if we are estimating the rate of change at x equals -4, we can use this line that they've drawn in for us, and the slope of that line would be our rate of change at that point. So who can tell me the slope of that line? What would it be? I like to find my next point. It's close on grid lines. Yeah, probably. Let's see. Let me erase my dot here. Yeah, because that's not exact. I had put 3/2, but that's actually not exactly on grid lines. So I don't think it's exact, but it's close to be going up 1, 2, 3, 4 over 3. So let's do 4 over 3. Now, that is an estimate. It is not necessarily the exact value at that point. Okay, 7 is going to ask us to sketch the tangent lines. And the tangent lines are going to touch just at one point, except sometimes the tangent lines, whenever you've got a graph, like for example, the tangent line right here is just going to be like a horizontal line. That tangent line does actually run into the graph again over here. It is tangent locally. It only hits one time at that point, and close to it. Sometimes when the graph goes up or down, it may run into the graph later. That's okay. It can still be called our tangent line because we're concerned at that point that it's just touching at that one place. So that's our tangent line at that point. Let's see. I'll use some different colors. Right here, we want a tangent line. This one's a little hard to draw. I don't like these 2 points they put in here. I think I'm going to go like that. I don't love this because this point right here, there's not going to be a lot of difference, right? It's going to be maybe something like this. That green line and the blue line are kind of close to each other. Let's draw in a tangent line right here. So that's going to be a line that just barely touches that graph like this. And then a colors that I've not used. Let's use this light green. This tangent line right here. Okay, and then they are not really going to ask you, in most cases, to estimate a tangent line with a lot of accuracy. What they do a lot of times ask you is to compare tangent lines. So it says, for example, 8. Does the graph of f appear to have a greater rate of change at 4 or 5? So if we go to our graph and look, 4 is right here, and so that's our pink tangent line. And then we've got 5 is right here. That's that light green tangent line. Which one appears to have a greater rate of change, the pink line or the green line? 4 or 5? That green at 5, right? It's very slight, but it's a little bit steeper, right? So we're thinking about which line is steeper in this case. And if you kind of think about that graph, at what it looks like, this graph is concave up, so it's getting a little bit steeper there. So x equals 5 would be our answer for this one. Okay? This just summarizes what we've talked about a lot. If our rate of change is positive, not our graph being positive, but our rate of change being positive, that means the graph of f is increasing. If we have a negative rate of change, that means our graph is decreasing. If we have a rate of change that's increasing, the graph is concave up. Rate of change is decreasing. Graph is concave down. All right. So let's look at this graph right here. It says the graph of f is shown above. Complete the blanks below to correctly describe the graph of f and the rate of change of f. So when it asks us about f, that is just what we're looking at, right? So this is the graph of f. It says the graph of f is f increasing or decreasing here? Increasing, right? So we are increasing. And is that concave up or concave down? Down. So down, we think of like this here. So this question that we're talking about, this part right here is asking us about f, right? So f, just the graph itself, as you go from left to right, that graph is increasing. It's going, your values are going up. Our rate of change is not necessarily increasing. So there's a difference in, and this is, we also do this in calculus because what we're actually talking about when we say rate of change is the derivative. And sometimes it's so confusing because it's hard to know whether you're talking about what you're looking at or the rate of change of what you're looking at. So this first line is asking us just about what we're looking at. So it is, this graph that we're looking at is increasing and it's kind of curved down. So we're just thinking, is this like curved down or curved up? If it was curved up, it might look more like this right here. And this one is kind of curved down for that. So it's just asking us about what we're looking at. But on the next part, it's not asking us about what we're looking at. Because the rate of change of f is blank, and the rate of change of f is blank. So, our rate of change here, we need to think about positive or negative. So rate of change, we can think of it a couple ways. We can either think about doing like our little tiny slopes like we've done, you know, like this. Or we actually now, if we wanted, since we've talked about it, we could talk about like the slope of those tangent lines at that point. Either one, it doesn't matter at this point. If we think about just doing those like little slopes that we've been doing right here, are the, I'm going to use a different color that shows up a little better, are the slopes of these little lines, are they getting steeper or less steep? They are getting less steep, right? That might be 1, that might be 1/2, that might be 1/3, right? But are they positive or negative? They're positive. Okay, so if the rate of change is positive, the graph is increasing. Or if the graph is increasing, the rate of change is positive. You could, depending on what they've given you. But that rate of change, it is positive, but are your values increasing or are they decreasing? Decreasing. So
these don't match up with the little thing at the bottom.
let me check.
Like, if that makes sense, but like that doesn't match.
So rate of change is positive, the graph is increasing. So, and if the rate of change is negative, the graph is decreasing. So this in red was talking about our rate of change. So our rate of change was positive, the graph was increasing. Where'd that go? So that part matches right here. Because what they did, they put rate of change first and the function over here. If the rate, and then On the next line, the rate of change is which is in red for us here. If it is decreasing, then we are increasing. Decreasing, we're concave down, which is matches here. Okay. And we didn't get that last little bit there. What I want you guys to do for me over the weekend is finish that worksheet that you guys had where we only did 1 through 7. Okay. So